we're going to think about derivatives in a new way and apply them to something that physically happens in real life. Obviously, you've read the title of this. This is talking about position, velocity, and acceleration. Those of you who are in physics, this will sound familiar because this is the math and the calculus that explains the different physics formulas you've probably been using all year long for projectile motion. The way that we have this is called a higher order derivative. It is essentially exactly what it sounds like. It is a higher ordered derivative. So you have a derivative, and then you can take a derivative of a derivative, and you can take a derivative of a derivative of a derivative. Those are called higher order derivatives.
So you're cubing a derivative.
Not cubing it. We are taking the derivative of a derivative.
Cube rooting.
Nope, we're taking the derivative of a derivative. The way that we notate this is with extra primes. So if we know that we say the derivative of f is f prime, the derivative of f prime is called f double prime. And so on. So you could have triple prime, fourth prime. I don't know actually how to say that out loud because it's called a jerk technically, but we don't worry about that. But all of these higher order derivatives actually give us different physical things for projectile motion and mechanics of physics. Position, velocity, and acceleration. So what we're going to start with for today is a position equation. So I'm going to use P of t because P for position, but sometimes people use x of t or s of t. It's just preference right there. The function itself is going to give the position of an object as a function of time t. So we're talking about distance from the x-axis that an object is traveling. So if you are walking, let's say that I started walking from right here. This is center. And I walk positively this way, and then I walk positively this, or negatively this way, and then I walk positive again. I can graph that as a position of where I am compared to my starting point. Think like a spring, how a spring goes down and up and down and up. That same sort of idea, but you can track an object compared to the x-axis. Now, velocity, we kind of know what velocity is. V of t is going to give a function of how fast and in which direction something is moving at any time t. Speed, however, is the absolute value of velocity. So speed, when you're talking about how fast something is going, you're usually talking about its speed because you don't care what direction. But technically, velocity tells you both a speed and a direction, a positive direction or a negative direction. Acceleration is the function a of t that gives how quickly the body or the object speeds up or slows down. A positive acceleration pushes an object, a negative acceleration pulls an object. What's the most obvious, common piece of acceleration that we deal with on a daily basis?
Cars.
Gravity or cars. So when you're talking about the acceleration in your car, you're talking about when you start driving, okay, and it is pushing you forward. That's why you're going forward. Gravity is going to pull you back down to the earth, correct? Gravity is a negative acceleration because it's pulling you down. You should not be driving 100 miles per hour, so let's back up.
There's a fly around 3 a.m. in the morning, and there's a fly in my car. How is it keeping up?
The cool part about all of this is that these are related to each other with derivatives. So if you have the position function and you take its derivative, you actually get the velocity of that object. Then if you have a velocity function and you take its derivative, you get acceleration. Bless you. Which means that acceleration is the second derivative for position. So when we get a position function, we can know at any point along that graph what is the velocity of the object and what is the acceleration of the object, which is really pretty cool because it gives us a lot of information about projectile motion. Does that sort of make sense how we're going to relate these things together? So if you are given a position function and I tell you take the derivative, the equation you get out of it is velocity. And if you take velocity, the one you just got, and you take the derivative again, that's the acceleration formula. Okay, well, let's hang on to it. Let's just try. So in our example here, it says an object for time greater than 0, which makes sense. We don't time travel in this class, so it's always going to be time greater than 0, is moving along the y-axis, so its position, P of t, measured in meters, is given by P of t equal to t cubed minus 9t squared plus 24t, where t is measured in seconds. So they gave us a position function. It wants us, in part A, to find the equations that show the velocity and the acceleration for the object. Okay, well, since we know that these are related via derivatives, if we wanted to find velocity, we know that velocity with regards to t is the same thing as p prime of t. So I just need to take the derivative of position to find the velocity equation. So what's the derivative of that position function?
Yes.
3t squared Great. If we were to graph that function, it would show me at any point along this graph of this object what its velocity is. Not its position anymore, but its velocity. If we want to find acceleration, acceleration is the derivative of velocity, which is the second derivative of position. But all that means that I need to do is take the derivative of this red velocity function, and I would have acceleration. What's the derivative of that red function? So now we have all three functions. By using derivatives, we have found, well, we were given position, then we found velocity, and we found acceleration. Yes? So we can use these functions to do things and to kind of describe the motion of this object through space. Not like space, but like space. I'm not talking about outer space necessarily, but just general 3D space. Part B says, during what time intervals is the object moving to the right? Okay, what does it mean for something to be moving to the right? What is positive? So to be moving to the right, that means that my velocity is positive. Because velocity tells me a direction as well as a speed. So if we want to know the direction, which is positive, we would just need to know when velocity is positive. Okay, cool. So I'm going to take the velocity equation, which is 3t squared minus 18t plus 24. And I'm going to say we want to solve for where this quadratic equation is greater than 0. Ooh, think about all that math we learned this year. We have to apply it to this situation. How do we solve a quadratic like this?
Ooh, multiplies to 24 and adds to 18. Or no?
You're on the right track, but let's do something easier to make these numbers smaller first.
Greatest common factor?
Yeah, these are all divisible by 3. So I'm just going to make all these numbers smaller. Oh, not, what? So that I'm working with smaller numbers.
Okay.
Now do what you were thinking. You were thinking of factoring it.
4 and negative 2. Or wait. 4, no. -4, -2.
-4, -2. Okay. So I'm going to switch this on purpose from a greater than sign to an equal sign, because when we were solving inequalities, we had to find critical numbers on a number line and then test the different intervals. So we know that the two critical numbers for this are the numbers 4 and the number 2. Those are going to be the places where our graph crosses the x-axis, and so we just need to figure out where it's positive. So we're saying, okay, here's my number line from 0 to infinity. I didn't start at negative infinity. I started at 0 because we don't time travel. Not in this class. So we have our critical numbers of 2 and 4. We just need to know what's happening in each of those intervals. Do y'all remember how we did this back in the day?
Oh, the loop and the loop and then the pop.
Opened or closed, yeah, something. Substituting numbers. We're making a sign chart.
It's that where like it's like negative, like a line, and then it's gonna be like little.
Yeah, you're on the right track. You're thinking the right thing. So what I want to do is I want to say, okay, what if I plugged in 1? Number 1 is in that first little interval. If I plugged in the number 1, it would be 3 times a negative number times a negative number, which means it's a positive number. Obviously, I could straight up plug in 1. That's not that hard to plug in, but I don't care about the number. I just care about whether it's positive or negative. What number could I plug in for the second interval? 3. So this would be 3 times a negative number times a positive number, which means that part's negative. And for that last interval, what number could I plug in? 5 is fine. You could plug in anything. So 10 would have been fine. 5 is fine as long as it is bigger than 4, which means we have 3 times a positive number times a positive number, which means this is positive. Okay, our question was, during which time intervals is this object moving to the right? So we ask ourselves, where is the velocity positive?
0 to 2 and from 4 to 30.
Exactly. So we're going to say the velocity is positive between 0 and 2, and then after 4 seconds, which we know would be parentheses 0, 2, union 4, infinity, but we're answering in words, not in math words, because they asked us a real life question. During what time intervals between 0 and 2 and from 4 on to infinity, whenever the object stops. So if we keep going with this idea, it says, find the velocity of the object when the acceleration is 0. Okay, the acceleration being 0 is something I can work with. Don't we have an equation for acceleration? We already found it earlier. It was the second derivative of position. What was that equation for acceleration? 6t minus 18. We're just wanting to see how to solve that for when it's equal to 0. That's a quick little solve. Add 18, divide by 6. What is t equal to? 3. So at time 3, the acceleration is 0. Cool, that's not what I'm asking for though. I'm asking for the velocity at that time. Find the velocity when the acceleration is 0. So what should I do with this number 3? Plug it in for t in the velocity equation. So we're going to plug in 3 here. Back in my velocity equation. And I trust we can type stuff in a calculator, so beep, 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 calculate. That's going to be negative 3 meters per second. Bonus question here. That's the velocity. What's the speed? 3. Remember that speed is the absolute value of velocity. So the speed is 3 meters per second because we don't care about direction. The negative 3 meters per second on velocity tells me it's going 3 meters per second down or to the left. That's a direction. Now I did skip over reading this part earlier up at the top, and I'm going to go back up there for a second. This last little section at the top says a particle's speed, which is something to do with its velocity, is increasing when the signs of velocity and acceleration are the same, and a particle's speed is decreasing when the signs of velocity and acceleration are opposite, because that means you have opposite forces working on each other, for my physics friends, instead of working in the same direction. So the question D says, is the speed of the object increasing or decreasing at t equals to 23 seconds? To answer this question, we need to know both the velocity and the acceleration at that time. So what should I be doing with the number 2.3 seconds? Plugging it in. So let's do this in an organized fashion. We'll go velocity, then acceleration. We're finding v of 2.3, which is 3 times 2.3 squared, minus 18 times 2.3 plus 24. We would calculate that. Again, I trust that we at this point can type stuff in a calculator successfully, especially when it's a quadratic. We would get negative 1.53 meters per second. That's the velocity of the object. So it has a speed of 1.53 meters per second going in the negative direction. But we also want the acceleration at that time. So we're going to plug 2.3 into the acceleration formula. 6 times 2.3 minus 18 is negative 4.2 meters per second squared. So since both of these answers are negative, What does that mean about the object? Is the speed of the object increasing or the speed of the object decreasing? Ooh, so the speed is increasing when they're the same, decreasing when they're opposites. These are the same, so we're going to say that this is increasing. So calculus is actually a really interesting way to dive into physics. A lot of you have taken physics without the math associated with it, and if you ever go to college and take a physics class, most likely it's going to be physics plus calculus at the same time because they are completely related to each other. The reason you have the formulas you had in physics is because of the calculus and the math behind it. Yes?